So now that we know how to solve homogeneous higher order differential equations, let's look at how we solve non-homogeneous higher order differential equations. There are several different methods to do this. One of them is called the undetermined coefficient annihilator method. There are two different methods for the undetermined coefficients. I happen to like the annihilator method. We call that an this nth derivative of y plus an minus 1, the nth minus first derivative of y, all the way down to a0 times y is equal to g of x, can be written as the linear operator or the differential operator L of y equals g of x. So this is the notation that we will be using in this material. So the nice thing about this notation is we can actually do what we call factor. So it actually can factor the operators. So just like you would factor in other things, we can factor here too. So looking at this, this would actually factor as d plus 4 and then d plus 2 of y. And so you've got that. You can also, by the way, the other way, you can also do d plus 2 and then d plus 4 because it is commutative. So these operators are commutative. And so you can actually think about having solving it this way. So we like this method. And in general, you can actually factor any of the linear operators, differential operators, as d minus root 1 times a parent polynomial operator. So we can do this if we want to. And this is where we kind of use the annihilator method, and we have what we call annihilator operator. And what that annihilator operator says is that if L of the function equals 0, then we say L annihilates the function. So as an example, if I take x and I take the second derivative of x, I will get 0. Because the first derivative will be 1 and the second derivative would be 2. If I have x squared, if I take the derivative 3 times, I will get 0. In fact, in general, if I have n minus x to the n minus first, if I take the nth derivative, I will always get 0. So in other words, this operator d to the n will eliminate any x to the n minus 1 function. So in fact, d of n, the nth derivative of operator, annihilates 1, x squared, all the way up to x to the n minus first. There's some other things that can annihilate. E to the a alpha x wouldn't annihilate with d to the n, but d minus alpha to the n does in fact annihilate it. And if you look at it, you did the derivative a bunch of times, you would see that this would work. It also eliminates x e to the alpha x, all the way down to x to the n minus 1 e to the alpha x. So as an example, d minus 6 annihilates e to the 6x. And that is because the derivative of e to the 6x minus 6 times the e to the 6x. So think of this as it's just a polynomial in a way. It really isn't. But you can think of it that way. So you can actually distribute that e to the x through the d minus 6. So you're taking the derivative of e to the 6x, and then you're going to subtract 6 times e to the 6x. Well, the derivative of e to the 6x is 6 e to the 6x. And 6 e to the 6x minus 6 e to the 6x is in fact 0. There's lots of other ones that annihilate. This is a fairly complicated one. The second derivative minus 2 times alpha times the derivative plus alpha squared plus beta squared all to the nth power annihilates e to the alpha x cosine of beta x, x e to the alpha x times cosine of beta x, all the way down to x to the n minus 1 e to the alpha x cosine of beta x. It also just works on sine of beta x. So, I mean, this works the same if it's cosine or sine. They work the same way. And so it's really looking at what one annihilates them and what that would be. And this is kind of a memorization kind of idea of which one does it. But we can actually go ahead and use this to help us. So I want to find the differential operator that annihilates 1 plus 7x minus 9x squared plus 3x cubed. Well, looking at this is just a polynomial. So any polynomial and is annihilated by just a derivative, and you just have to figure out how many derivatives you need to do. So this is x to the third. It's the highest order of this polynomial. So that means we need to take the fourth derivative. So the fourth derivative of 1 plus 7x minus 9x squared plus 3x cubed will be 0. And you want to try this out, see that the first derivative of 1, of course, is 0. The second derivative of 7x is 0. The third derivative of 9x squared is 0. And the fourth derivative of 3x cubed is, of course, 0. So it all works out and it'll happen and you get that. Now let's try x e to the minus 2x. Again, this is one where we're going to have d minus alpha. Alpha is what is ever up in the exponential of your e. So it's whatever's being multiplied by the x. So in this case, it's a minus 2. So instead of being d minus a negative 2, it's just d plus 2. We'll annihilate x e to the minus 2x. The only thing is that because of this x here, we're going to have a couple more things going on. So we actually need 2 so we can get rid of that x. Because remember, x is annihilated by the derivative right beyond it. So x to the first means I need a second derivative. So that's where that 2 comes into place, is that this x won't be eliminated just with a first there. It needs a second derivative. And again, you can practice it and you can try it out and see if it works, and it will in fact annihilate them. So let's try 5e to the 6x minus 7x to the fourth. Well, these are not both polynomials. This one was just an exponential, x times an exponential. This one's a combination of an exponential and a polynomial or power function. And so when we go to do this, we need to figure out what annihilates this 7x to the fourth. Well, that would be d to the fifth. That would eliminate that term. We also need to figure out what eliminates the 5e to the 6x. Well, that would be d minus whatever's in front of the x. And we don't need any power because there's no x here. This is just 5e to the 6x. And these two together, multiplied together, will eliminate this. So this is your elimination. Your annihilator is the d to the fifth, which annihilates the 7x to the fourth, and d minus 6, which annihilates the 5e to the 6x. So if you have multiple terms that you're dealing with, you're going to find the annihilators and multiply them together. The last one I want to look at is 5e to the negative 3x sine of 4x plus 6e to the negative 3x cosine of 4x. I want to eliminate that, or annihilate that, I should say it that way. So again, this is a little bit more complicated one. If you go back and look at what annihilates e to the x times cosine of beta x, that's going to be d squared minus 2 alpha d, where alpha is whatever's in the exponential, plus alpha squared plus beta squared, but beta is inside the cosine. And again, this works for sine or cosine. In fact, they work together. So I happen to have a sine and cosine, so I only need to have one of these because it'll eliminate both of them. So what I've got is I've got a d squared, because that's the very first one we started with, minus the 2 times the alpha. The alpha is minus 3 times d plus the alpha squared, which again is minus 3 squared, plus the beta squared, and beta is inside the sine and cosine. Happens to be 4, and that's also squared. And that will eliminate all this. Now, I would actually multiply this all out and see what you get. This multiplies out into d squared plus 6d plus 9 plus 16 is 25. That's a little bit easier way to look at it, and that will also annihilate all of this. So if I were to use that on this term, it would make it equal to 0. All right, now that we have an idea of the annihilation and what we would use, we can now move on to how we use this. And again, this is called the method of undetermined coefficients. Is what we're going to be using. And the first thing we're going to do is we're going to first solve L of y equals 0. So we're going to first look for the associated homogeneous equation and solve that. Then we're going to put that back in. Once we know what that y is, we're then going to annihilate that y to find out what g of x and equal that to g of x. And then that annihilation, you're going to figure out what annihilates, because that annihilates y. But you're also going to find out what annihilates g of x. So that's the next thing to do, is once you found out what is you're solving the associated homogeneous, that'll tell you what annihilates the y. You're then going to figure out what annihilates the g of x. And so L of y equals g of x, and then you're going to take L1 of the L of y equals L1 of the g of x equals 0, and then you have a new homogeneous equation to solve. And what you're going to do is you're going to discover, and discover is an interesting word, you're going to discover the form of y sub p. When you substitute y sub p into that L of y, you get g of x. And then you're going to find your constants, because remember, y of p is the solution to the non-homogeneous that creates the g of x, and it is constant free. So our job is to find out what that is. So let's go ahead and do an example of this. Let's solve this equation, y double prime minus 5y equals x squared minus 2x. This is what I want to try to solve. So again, the very first thing I'm going to do is solve the associated homogeneous. And the associated homogeneous is y double prime minus 5y equals 0. Homogeneous just means you replace the g of x with 0. We know how to solve this already. This is, we'll get the associated equation, which would be m squared minus 5 in this case. That gives me m is equal to plus or minus the square root of 5. So that means my complementary solution, which is the solution to the associated homogeneous equation, the complementary solution would be C1 e to the square root of 5x plus C2 e to the minus square root of 5x. So we at least know that part. Well, that's great. We could have done that before. So what we now need to do is we need to figure out what annihilates my g of x, what annihilates x squared minus 2x. Well, looking at this, x squared would be eliminated by the third derivative. So d cubed of x squared minus 2x does in fact annihilate that, gives me 0. Okay. So what I'm going to do is I'm going to rewrite my differential equation y double prime minus 5y inside of a, with the notation of differential operator. So I'm going to have d squared minus 5 of y is equal to x squared minus 2x. And now that I know what annihilates the x squared minus 2x, I'm going to basically operate that on both sides. You can think of this as multiplying both sides by d squared, but I don't like to think of it that way because it really is operating d cubed on both sides. I'm taking the third derivative of both sides. So when I do that, I get d cubed times d squared minus 5 of y is equal to 0. Well, this is a homogeneous equation. We already know how to solve these. If you wanted to, you could multiply this together and see that you've got the fifth derivative of y minus the third, 5 times the third derivative of y, which would actually give you m cubed times m squared minus 5 of y. So your associated, and actually I don't want the y in there, your associated equation is m cubed times m squared minus 5 equals 0. So what I see is I've got m equals 0, and that has multiplicity 3, because I have a third power there. And I also have m is equal to plus or minus the square root of 5. So now I can see, oh, I have a new equation. My solution now is y is equal to c1 e to the square root of 5x plus c2 e to the negative square root of 5x plus c3 times x e to the 0, which is just 1, plus, because it's multiplicity, remember you have c4x plus c5x squared. So m equals 0 is equal to the 0x, which is just 1, but then you need an x and you need an x squared. Well, here's the really cool thing about all this. The really cool thing about all this is that this c1 e to the square root of 5x plus c2 e to the negative square root of 5x, where's your y sub c? We already found that. Which means your y sub p is everything that's left. Because we already knew that these two terms together were my y sub c, because that's where we did that first. We found that out up here. We found our y sub c up here by finding the associated homogeneous equation. Now that we know that that's it, everything left over must be your y sub p. Cool. So this is what we mean by discover it. You are going to write what your equation would be. You're going to take out what the y sub c is, and everything left over is your y sub p. Okay, so we're not done yet. So let's go ahead and keep going on this problem. So now that we've done that, we now know that y sub p is c3 plus c4x plus c5x squared. We now know that that's what it is. And we know that it will in fact solve the differential equation. Remember, my differential equation was y double prime minus 5y equals x squared minus 2x. We know that this y sub p has to satisfy this differential equation. So if we know something is a solution to a differential equation, we know we can plug it in and show that one side equals the other. So let's do that. Let's plug this in. First thing I notice is I need the second derivative. So let's find the first derivative. The first derivative of y sub p is going to be c4 plus 2c5x. And the second derivative is going to be 2c5. And then we just plug that in. So we have 2c5 minus 5 times y, which is c3 plus c4x plus c5x squared, is equal to x squared minus 2x. A really neat thing is that the coefficients of your power functions on one side of the equation has to equal the coefficients of the power functions on the other side of the equation. For that matter, any functions. If you had e to the x on one side, you'd have to have that equal to the e to the x coefficient on the other side. Sine, cosine, all of that works out. So let's first try to simplify this a little bit and find out what are our coefficients of the, in this case, we only have power functions. So we have, let's see, we have a 2c5 minus a 5c3. Those are my constants. Minus a 5c4x minus a 5c5x squared equals x squared minus 2x. So my coefficient of x squared on the left-hand side of the equation is minus 5c5. My coefficient of x squared on the other side of the equation is 1. So that tells me that my c5 must be negative 1/5. My coefficient of x on the left-hand side of the equation is minus 5c4. My coefficient of x on the right-hand side of the equation is minus 2. So that tells me that c4 is 2/5. My constant on the left-hand side of the equation is 2c5 minus 5c3. My constant on the other side of the equation is 0. So I already know what c5 and c4 is. All I got to do is find c3. So c3 is 2/5 C5, but we know C5 is 1/5. So we know C3, or negative 1/5, is 1/5 times 2/5 times negative 1/5. So we get that that one is negative 2/25. So we now know what the y sub p is. Y sub p was C3, which is negative 2/25, plus C4, which is 2/5 x, plus C5, which was negative 1/5. So let's make this a negative 1/5 times x squared. And now we can get y, because y was y sub c, which we know was C1 e to the square root of 5x plus C2 e to the negative square root of 5x. And then we have minus 2/25 plus 2/5 x minus 1/5 x squared. And there is your solution to this differential equation. If you had an initial value problem, you could find out what C1 and C2 are, but we don't know what those are. We don't have initial conditions, so we can't find those. All right, let's try one more example of this, just showing you how this works. So the third derivative of y plus 5y prime is equal to e to the x cosine of 2x. So again, the very first step we're going to do is we're going to solve the associated homogeneous equation. And the associated homogeneous equation means you just set it equal to 0. So y triple prime plus 4y prime equals 0. Then this would be m cubed plus 4m equals 0 when you get the auxiliary equation. And so then if I factor that, I get m times m squared plus 4 equals 0. So m equals 0 and m equals plus or minus 2i. All right. So now when we go to do our y sub c, this is the complementary solution. It's the solution to the associated homogeneous equation. It would be C1 e to the 0, which of course is just C1. Negative plus or minus 2i gives me cosine and sine. So I know I'm going to have a C2 cosine of 2x plus C3 sine of 2x. There's no real part, so that's why there's no e. It's just an imaginary part. Okay. So now we have that. Now what we have to do is try to figure out what annihilates e to the x cosine of 2x. So what annihilates that is always a d squared minus the alpha level, which the alpha is whatever's in front of the e to the x, and e to the whatever x, in this case it's a 1x. So minus 2 times that 1 times d, plus my alpha squared, plus my beta squared, and beta is whatever's in front of inside the cosine. So it's cosine of 2x, so that would be 2 squared. So that is d squared minus 2d plus 5. That annihilates my e to the cosine of 2x. Okay. So that says that what we're going to now do is we're going to take that annihilator, which was d squared minus 2d plus 5, and operate it on my differential equation. And I'm going to rewrite my differential equation in terms of the differential operator. It was y cubed, so that's the third derivative, plus 4 times y prime, so that's the first derivative, times of y equals the differential operator on my e to the 2x, or e to the x cosine of 2x. And so we know we get d squared minus 2d plus 5 times d cubed plus 4d of y equals 0 because it annihilates it. I would not multiply this all back out again because we will be factoring when we get to our auxiliary equation. In fact, let's get our auxiliary equation. Our auxiliary equation is m squared minus 2m plus 5 and m cubed plus 4m equals 0. What's really nice about this method and writing this in the differential operators is you can see you're just replacing your d's with m's. And remember the y goes away because y is equal to e to the ax or the mx. So this is why this happens this way. It's that same kind of idea. Now we just have to solve all these. M squared minus 2m plus 5 factors as m equals 1 plus or minus 2i. The other one we already know is m equals 0 and m equals plus or minus 2i. All right, so now we can get our y. And I don't really care what order you write this in. You can do it in any order you want. This m1 plus or minus 2i will give me a c1 e to the x, because my real part is 1, so there's a 1 in the e, cosine of 2x, because there's 2 there, plus c2 e to the x sine of 2x. My 0 gives me, call it c3 e to the 0, which is just 1. My plus or minus 2i gives me c4 cosine of 2x plus c5 sine of 2x. And this is where we get to discover what y sub p is. I remember from what I've done before, my c3 plus c4 cosine 2x plus c5 sine of 2x, that was my y sub c. That means everything left over is your y sub p. So this is what we mean by discover it, is you're going to figure out, you know what your y sub c is, because the first thing you did was find that. Once you know what that is, you know everything left over is your y sub p. So you're discovering that. And again, that then has to satisfy the differential equation. So that means that we can, in fact, plug it in to find out what those constants are. So you'd find y sub p prime, which is not the nicest of things, but it turns out it's not too bad. That would be c1 plus 2c2 e to the x cosine x, cosine of 2x, plus c2 minus 2c1 e to the x sine x. So you're just doing product rule derivatives and simplifying it. Your y sub p prime, double prime, would be 4c2 minus 3c1 e to the x cosine 2x plus 2c1 minus 11c2 e to the x sine of 2x. And we're doing the triple, so we're going to do y triple prime. And that will be minus 11c1 minus 2c2 e to the x cosine 2x plus 2c1. Oops, I just realized I got these backwards here. In my y double prime, the second term should have been negative 4c1 minus 3c2 e to the x sine x. And then this last one, y triple prime, is 2c1 minus 11c2 e to the x sine of 2x. All right, so we just found all those nice little derivatives. Now we're just going to plug those in and find out what we get. So as a reminder, our differential equation is y triple prime plus 4y prime is equal to e to the x cosine of 2x. So we're going to go ahead and put into this equation your triple prime, which was minus 11c1 minus 2c2 e to the x cosine 2x plus 2c1 minus 11c2 e to the x sine of 2x plus 4 times y prime, which was c1 plus 2c2 e to the x cosine 2x. And I'm going to go ahead and just distribute that 4 through. So plus 4c2 minus 2c1 e to the x sine of 2x. And that should equal e to the x cosine of 2x. Okay, so now all you have to do is multiply all this out, collect all your like terms. When I do that, I get minus 11c1 minus 2c2 plus 4c1 plus 8c2 all times e to the x cosine of 2x. And then I have plus 2c1 minus 11c2 plus 4c2 minus 8c1 all times e to the x sine of 2x. And remember that all equals e to the x cosine of 2x. Again, a really nice thing is that the coefficients of your functions on one side has to equal the coefficients of your functions on the other side. We have a function of e to the x cosine of 2x on both sides of the equation, so their constants have to equal each other. The coefficients have to be the same. So minus 11c1 minus 2c2 plus 4c1 plus 8c2 has to equal 1. And we could have combined those together. In fact, let's go ahead and do that. That would be minus 7c1 plus 6c2 equals 1. And the constants, the coefficients of the other function, e to the x sine of 2x, has to equal the coefficients of the other of that same function on the other side. But there isn't an e to the x sine of 2x on the other side. So it must be 0. So that must mean 2c1 minus 11c2 plus 4c2 minus 8c1 has to equal 0. And again, I'm going to combine my like terms here, and I end up with minus 6c1 minus 7, or plus, sorry, the minus 7c2 equals 0. So I now end up having the nice little system. I have a system of minus 7c1 plus 6c2 equals 1, and minus 6c1 minus 7c2 equals 0. So I just have a system of equations. I just have to solve that system. I don't care how you solve that system. You can use matrices. You can just add these together by multiplying by coefficients. I'd multiply the top by 7 and the bottom by 6, and add them together and solve for these, and you'd find them. I'm not going to show you how to do that. You all know how to solve systems equations here. C1 turns out to be negative 7/85. C2 turns out to be 6/85. So we now know what y sub p is. Y sub p is negative 7/85 e to the x cosine of 2x plus 6/85 e to the x sine of 2x. So now I can get my y. My y is y sub c plus y sub p. Y sub c, we already knew from some time ago, was c1 plus c2 cosine of 2x plus c3 sine of 2x. And again, this is your complementary solution. It will have your constants in there. You need an initial value problem to find those constants. But then the particular solution is minus 7/85 e to the x cosine of 2x plus 6/85 e to the x sine of 2x. So there's your solution. Again, if you had an initial value problem, you could find your 3 constants, but that's all there is to finding the solution.